Alright, so hello, my name is Paul once again, and for my last Teach Me Something assignment, I want to explore what aminoacyl tRNA synthetases are, as I get a little confused every time about the chemical processes of these enzymes. But first, to understand what tRNA synthetases are, I need to review what tRNAs are in general. So let's get started here. So tRNAs will be made from the nucleus, as most RNAs will be synthesized. But the basic function of tRNAs will just be to serve as intermediaries, which basically means it's going to act as a link in order to bring about a process, which in this case is translation. In order to do this, it will bring amino acids to the messenger RNA, the mRNA, and the ribosomes. As for the structure of tRNA, it would probably be better if I could just show you a figure and do a quick overview of how it works. So once the mRNA has been secreted from the nuclear pores and is into the cytosol, the small ribosomal subunit in blue in this figure here will attach itself to the 5' end. However, the tRNA will place itself onto the P site, aka the peptidyl site, which is crucial in the process of initiation because this tRNA and other tRNA will have an anticodon. In this case, the initiator tRNA will have an anticodon of UAC, so that it matches up with the start codon that we know as AUG. Additionally, this initiator tRNA will have an amino acid called methionine, which corresponds with the start codon. And so after the small ribosomal subunit that contains this initiator tRNA binds to the mRNA, it will start scanning along the single strand to find the start codon, AUG. And once it does, the large ribosomal subunit will come attach itself to the small ribosomal subunit and create these sites called the E site, also known as the exit site, the P site, which again is where the initiator tRNA will find itself, and the A site, where the tRNAs containing other amino acids will come in and join the process of translation. So, all in all, the small ribosomal subunit with the initiator protein will sit on the 5' end of the messenger RNA and begins searching for the AUG start codon. Once this happens, the large ribosomal subunit will sit on top of the small ribosomal subunit and create the E, P, and the A sites. A new tRNA with a different amino acid that has a anticodon complementary to the second mRNA codon will bind to the A site, and the amino acid from the initiator tRNA that is sitting in the P site currently will be transferred to the tRNA that is in the A site. And after this happens, translocation will occur, in which the tRNA within the P site will be shifted over to the E site, where it will exit the ribosomal subunits and pick up the same amino acid from the cytosol and continues to build. Additionally, the tRNA that was originally in the A site will now move over to the P site, and pretty much this process keeps happening over and over again, building that polypeptide, that protein, by adding amino acids to the growing chain in a process called elongation. But it will stop this process of translation when it encounters a stop codon where translation stops and the polypeptide will be released. Now, we know that the function of how tRNA works within the process of translation, but I wanted to explore the question of how does this tRNA obtain these amino acids? So, like, do they pre-exist on a tRNA, or do tRNAs have to go through looking for a correct amino acid with respect to their anticodons? Well, in this case, there are going to be enzymes called aminoacyl tRNA synthetases that will be necessary in catalyzing the linkage of the correct amino acids to each corresponding tRNA. Now, cells are typically going to have 20 different aminoacyl tRNA synthetases, one for each of the 20 amino acids used in translation. However, how do these synthetases function is the real question here. Well, I found out that they will catalyze the attachment of the amino acids to their corresponding tRNAs via a ester bond, which is accompanied by the hydrolysis of ATP to AMP. So, of course, I believe that this would probably be better if I could just apply this information towards a figure. So, here's one, and the aminoacyl tRNA synthetase will be represented here in blue, and the substrates consisting of the amino acid and ATP will enter the active sites of this enzyme, where the amino acid and the AMP are joined together, but this is only possible through the breakdown or the hydrolysis of this pyrophosphate here to the two inorganic phosphates. And if I do remember from your lecture, I think the reason why this happens is so that the reverse reaction will not occur, and pretty much the inorganic phosphate will start to accumulate within the cytoplasm and will be used by the ATP synthases in the electron transport chain to create ATP once more. So moving on here, a tRNA will come in, and in the bond that was once between the amino acid and the AMP will now be shifted over between the amino acid and the tRNA. But the AMP is essentially lost to the cytoplasm in this process because it's basically what is needed to make the bond between the tRNA and the amino acid. Now, saying all of this, how does this synthetase know what specific tRNA will bind to the corresponding amino acid? Well, it's pretty much going to be this 3' acceptor stem, or the anti-codon triplet that will allow the synthetase to know what tRNA needs to become linked to the corresponding amino acid that the synthetase does. Synthetase is currently holding on to. And after it has correctly binded, the synthetase is smart enough to go ahead and proofread the final product to make sure that the correct amino acid is being used. And once this does happen, the tRNA with the binded amino acid will be released, which is this released tRNA with the binded amino acid is also called a aminoacyl tRNA, where it's going to be ready to be used in the process of translation. Not to mention the aminoacyl tRNA is also called a charged tRNA because it has a high energy bond, which I've read in my book that the bond provides enough energy to drive a formation of the peptide bond that will attach amino acids to a growing chain. So, in summation of these enzymes, this enzyme will pretty much be responsible for not only linking tRNAs to their corresponding amino acids, but will be also be responsible for relinking tRNAs that have left the E site from those ribosomal subunits. Next, the binding process will require the hydrolysis of the ATP to the AMP to link that AMP to the amino acid, while the pyrophosphate will be hydrolyzed to the inorganic phosphates to prevent the reverse reaction from happening. Moving along here, there will be proofreading mechanisms where the synthetase will recognize the correct tRNA that is needed to bind to the amino acid that the enzyme is holding on to, and in addition, the synthetase will further proofread the final product to make sure the correct amino acid is being used. And lastly, the enzyme is pretty much going through this process called amino acid activation, where it not only links any amino acid to its proper tRNA, but will also activate the peptide bond formation due to the sufficient amount of energy that the charged tRNA now has. So, as always, I just want to say thank you for watching. I think these assignments have really helped me out this semester, because I usually choose subjects or like topics that are kind of like foggy to me. So doing these assignments usually lets me read more about them and try to explain how they work in general. So pretty much in the process of this, I learn and pretty much know the material. So yeah, once again, thank you for watching.